In the final segment of this tutorial, I'd like to return to thinking in a more principled way about the relationship between early life experience, patterns of electrical activity in those developing neural circuits, and then the influence of neurotrophins. Well, do you remember Hebb's postulate? We talked about this when we first considered synaptic plasticity back in Unit 2. Hebb's postulate states that the coordinated activity of a presynaptic terminal and a postsynaptic cell would strengthen the synaptic connection between them. And conversely, uncoordinated activity between synaptic partners would weaken their synaptic connections. Well, these aspects of Hebb's postulate, I think, is very aptly summed up by my late great colleague here at Duke, Dr. Larry Katz, who said that neurons that fire together wire together. Now let's try to relate what I've been describing for you as the important role of sensory motor experience in cortical development in terms of Hebb's postulate. Well, Hebb postulated that what was important for the development of strong connections is the coordination of activity. Well, I would suggest that one important source of coordination is normal sensory motor experience. So this kind of experience can structure the activity in sensory and motor pathways and provide an important source of spatial and temporal structure that might essentially provide for the coordination of pre- and postsynaptic elements. So imagine, for example, the developing visual system that's encountering patterns and objects that are defined by the orientation of their boundaries. Some of these objects are moving relative to others. This provides a rich source of spatial and temporal cues that can drive the coordination of firing in the circuits that are being constructed in early life to compute properties such as orientation and direction selectivity. So for those circuits that are being activated, we imagine that there's coordination between the presynaptic and postsynaptic elements. Very likely we're satisfying our spike timing dependent plasticity rules for the strengthening of synaptic connections. That is, for those circuits that are being shaped by this activity, there's presynaptic activity that is driving postsynaptic activity. Those circuits where the presynaptic input fires prior to the postsynaptic cell by a short period of time are likely to be reinforced. Now consider the impact of sensory deprivation, be it total deprivation or perhaps abnormal deprivation. One way to understand the impact of abnormal experience is that we are failing to provide the spatial and temporal cues that are essential for sculpting activity within these developing cortical networks. Perhaps we are failing to drive the successful coordination of pre- and postsynaptic elements. And with essentially the introduction of noise into the activity patterns of these developing networks, I think we are more likely to favor uncoordinated activity between pre- and postsynaptic elements, with more often than not a postsynaptic neuron firing in advance of any given presynaptic input. That might favor the depression of synaptic connections, perhaps even the elimination of synaptic connections that otherwise would have anticipated normal experience and a synergy that would allow for self-organization and the impact of experience to work hand in hand to build up functional neural networks. If anything, the neural networks that are built up will be adapted to the abnormal experience that's driving activity in that network. Well, Hebb's postulate allows us to account for the early impact of shaping activity within developing neural networks, but the long-lasting impact is going to require additional molecular signals, and perhaps that's where neurotrophins come in. So let's try to weave into this story what we learned in our last tutorial about the importance of neurotrophins for promoting the growth and survival of neurons and their connections. One important point to emphasize is that the production and release of neurotrophins is activity dependent. Secondly, that neurons that are connected and coordinated would likely strengthen their interconnections and be nourished via the release of neurotrophin in an activity-dependent manner. And that neurotrophin will be taken up by the presynaptic elements and will have local effects on those terminals that are binding neurotrophins to their receptors. But the internalization and the retrograde transport of those endosomes back to the cell bodies can have a long-lasting impact on the viability of the cell that is being so nourished. So in this way, we think that neurotrophins become an important mediator of the long-lasting benefits of coordinated activity between pre- and postsynaptic elements in developing circuits. Now, the converse might also help us to understand the impact of abnormal experience. So for those circuits that are driven by abnormal experience, that is, there's functional connectivity but poor coordination, these connections will be weakened as a consequence of the conditions that would favor long-term depression. But these connections are also going to be weakened and eventually eliminated because they will fail to acquire this neurotrophic substance that is released in limited quantity. So these connections are going to fail to thrive because they're being deprived of sufficient neurotrophic support. Now we can extend these ideas really across the lifespan and suggest that even in maturity, neurotrophins become an important mediator of plasticity as the brain continues to adapt to sensory motor experience. So in the mature system, the regulated secretion of trophic factors continues to help shape the structure and function of neural connections, and this is especially true in response to injury or to adaptations to new patterns of experience, the kinds of patterns that might be engendered as we try to learn a new skill, or perhaps as we try to accept the challenge of learning medical neuroscience. So hopefully hanging with me through these many hours of tutorials and all the great studying you've done on your own has promoted the release of neurotrophins in circuits that are helping to make you a more efficient and effective learner, and hopefully to learn in a way that allows you to apply this new knowledge in a variety of settings. Now, in the final tutorial in Unit 5 on the changing brain, we're going to focus a little bit more on how the brain is responding to injury and disease. But one factor that I want to help you understand is that in the brain that's dealing with some kind of injury, neurotrophins have an important role to play in promoting adaptive plasticity. So in the recovering brain, we know that the activity of certain neurotrophins like brain-derived neurotrophic factor, BDNF, this has been linked to adaptive plasticity in circuits that are mediating functional recovery. What I find especially fascinating are recent genomic studies that suggest that as human beings, there are variations in our BDNF gene that might render cortical circuits more or less adaptive to motor challenges or cognitive challenges, and especially in our capacity to respond to injury. So neurotrophins may provide us with a wonderful therapeutic opportunity to increase the adaptive plasticity that might facilitate functional recovery following injury to the brain. So I'd like to conclude this tutorial with one thought that sort of drives these basic science concepts into clinical practice. And whether you aspire to a career in the health professions or find yourself there already, I want you to know that whatever you do with your patients and clients that are living with brain injury, that is, the kind of sensory motor experience that you might prescribe for your patients in the course of their activities of daily living or a more structured program of rehabilitation. This is powerful. This has the potential to modulate the production of neurotrophins and shape the plasticity of circuits, be it a child with ongoing development and construction of neural circuits or an adult where developmental programs are being re-engaged and expressed anew as a compensation of the brain to injury and disease. Well, I do a fair amount of my teaching here at Duke with students in the allied health professions, in particular with students that are becoming doctors of physical therapy. And I love to talk about this point with that group of learners in particular, because for those groups of students, they're entering a profession that neither medicates the nervous system nor does it cut the nervous system. And I might suggest that they have opportunity to do something even more powerful. They get to structure the sensory and motor experiences of the human body as a therapeutic modality that has the power to alter the structure and function of circuits in the brain and the spinal cord. Even without pharmacological intervention or surgical intervention, it's possible to shape ongoing patterns of activity that can promote functional adaptation. And the more we learn about these basic neuroscience principles of plasticity and the interactions among these various forces that shape the structure and function of circuits in the brain, the more effective can our interventions be. Well, thank you for hanging with me in this tutorial and for giving me an opportunity to share in some measure of detail some of the research findings that I've been privileged to be part of over the last decade or so. I think the upshot for me, and I think for most of my colleagues in the world of developmental neurobiology, is that we're entering a wonderful era where we are discovering more about the rules that govern the plasticity of circuits in early life, and it's empowering us to understand best how to promote the adaptation of circuitry to maximize health and wellness, especially in critical periods of brain development. And we trust that what we are learning about early brain development can apply throughout the lifespan, especially in the context of neural circuits that are adapting to injury or disease. So one of the great promises of developmental neuroscience is the discovery of basic principles that can apply throughout life as the brain re-engages programs of brain development as a means of coping with disease and injury. In our final tutorial in Unit 5 on the changing brain, we will focus on how the brain continues to change out of the early years of postnatal life through adolescence and into adulthood. And we'll spend much of our time thinking together about how the nervous system responds to injury and disease. So I look forward to that final discussion with you that will put a conclusion on Unit 5, and that will allow us to progress on into the final stage of the course as we embrace the complex brain functions that will be the focus of Unit 6. So I'll see you there shortly.